Welcome to the world of modern software architecture. Everyone talks about microservices like they are the ultimate solution to every scaling problem. You've probably seen the diagrams, a series of neat, isolated boxes, each doing one thing perfectly. In theory, it's a dream. You can scale parts of your app independently, use different programming languages for different tasks, and deploy updates without taking down the whole system. But here is the catch. What works on a whiteboard often turns into a distributed nightmare in production. Moving from a monolith to microservices isn't just a technical change. It's a fundamental shift in how you handle data, networking, and even your company culture. Today, we are diving deep into the hidden costs and the brutal realities of why microservices are so hard in real life. The first hard truth is the network. In a monolith, when service A calls service B, it is an in-memory function call. It is nearly instantaneous and almost 100% reliable. In microservices, that same call travels over the network. This introduces two massive problems: latency and partial failure. Every network hop adds milliseconds, and those milliseconds stack up. If your user's request triggers a chain of 10 microservices, that latency becomes visible to the user. Even worse, the network is unreliable. Packets get lost, connections time out, and services crash. In a monolith, if the process is up, the call works. In microservices, you have to write complex logic like retries, circuit breakers, and timeouts just to handle the fact that the network might fail at any moment. You are no longer just writing logic. You are managing a distributed system. Then there is the nightmare of distributed transactions. Imagine a customer places an order. You need to charge their credit card, update the inventory, and send a confirmation email. In a monolith with a single database, this is easy. You wrap it in a single SQL transaction. Either it all succeeds or it all fails. In microservices, the payment service has its database, and the inventory service has its own. You cannot use a standard database transaction across them. If the payment succeeds but the inventory update fails, you are in a state of data inconsistency. To fix this, you need complex patterns like sagas or two-phase commits. You have to write compensating transactions, code that manually undoes the previous steps if something down the line fails. This adds layers of boilerplate and potential bugs that simply do not exist in a monolith. Observability becomes a massive challenge. When a user reports an error in a monolith, you check one log file. You see the stock trace and you know exactly where it happened. In microservices, a single request might bounce through 15 different services. If something goes wrong, where did it happen? Was it the gateway, the authentication service, the database proxy? To solve this, you need distributed tracing. Every request must be tagged with a unique correlation ID that follows it through every service. You need centralized logging systems like ELK or Splunk and complex monitoring dashboards. Without these, you are essentially flying blind. You spend more time being a detective trying to piece together what happened across a dozen different servers than you do actually writing new features. Let us talk about operational complexity. In a monolith, you deploy one artifact, one CI/CD pipeline, one process to monitor. With microservices, you are managing a fleet. You need container orchestration, usually Kubernetes, which is a massive learning curve in itself. You need service discovery, so service A can find service B's dynamic IP address. You need load balancers, API gateways, and secret management for every single service. This is often called the microservices tax. You might only have 5 developers, but suddenly you need 2 full-time DevOps engineers just to keep the infrastructure running. If your team is small, the overhead of managing the environment can completely outweigh the benefits of the architecture. You end up spending 80% of your time on plumbing and only 20% on the actual product. Data consistency is another beast. In a distributed system, you have to choose between consistency and availability. This is the CAP theorem. Most microservices choose eventual consistency. This means that when you update your profile, your friend might not see the change for a few seconds. While this sounds fine for a social media app, it is terrifying for financial or medical systems. Developers now have to think about stale data. Your code has to be written to handle the fact that the data it just read might already be out of date. This adds a level of cognitive load that makes simple features much harder to implement correctly. You are constantly balancing the speed of the system against the correctness of the data.
Conway's law states that organizations design systems that mirror their communication structure. Microservices are often a solution to a people problem, not a technical one. If you have 500 developers, you cannot have them all working on one codebase. You split the code so you can split the teams. But if your teams do not have clear boundaries and autonomy, microservices will make things worse. You end up with distributed monoliths, where every change in service A requires a synchronized change in service B and C. This is the worst of both worlds, the slow deployment of a monolith with the complexity of microservices. To succeed, your teams must be as decoupled as your services, which requires a massive cultural shift in how the company operates. Security in a microservices world is a different beast. In a monolith, you have a hard outer shell, a firewall, and a load balancer, and everything inside is trusted. In microservices, the perimeter is gone. Every service endpoint is a potential entry point for an attacker. You have to implement zero trust. Every service must authenticate and authorize every single request from every other service. Managing certificates, rotating API keys, and handling identity across dozens of services is a massive undertaking. If one minor service is compromised, an attacker can move laterally through your entire system if you haven't secured the internal east-west traffic. You are moving from securing one big door to securing 100 small windows. Testing also becomes exponentially harder. How do you run an end-to-end test when the system consists of 20 services? You can't easily spin up the entire environment on a developer's laptop. You rely on mocks and stubs, but mocks can lie. If the team owning the shipping service changes their API and doesn't tell you, your tests will pass, but the system will break in production. This is why contract testing is essential. It ensures that the provider and the consumer of an API agree on the format of the data. But setting up contract testing is yet another tool and another process to manage. Testing in microservices often feels like trying to test a car while it's being built by 5 different factories at the same time.
So, should you use microservices? The answer is only if you absolutely have to. For most startups and small teams, a well-structured monolith is almost always the better choice. It is faster to develop, easier to test, and cheaper to run. Microservices are not a free lunch. They are an expensive tool for solving specific scaling problems. Use them when your team is too large to coordinate or when specific parts of your app have radically different scaling needs. But remember, every microservice you add is a new piece of infrastructure you have to maintain forever. Don't build a distributed system until you have a distributed problem. Start simple, stay monolith as long as possible, and only split when the pain of the monolith exceeds the pain of the network.